What is going on, guys? Welcome back. In this video today we're going to implement gradient descent from scratch in Python, and I'm going to try to give you an intuitive as well as a mathematical understanding of what is actually happening. So let us get right into it. Alright, so we're going to implement gradient descent from scratch in Python today, and for this we're only going to rely on two external Python packages, one being NumPy so that we can work with NumPy arrays, and the second one being Matplotlib so that we can visualize the process once we have the implementation ready. And if you don't have these two packages installed, you can just open up your command line and type pip install or pip3 install NumPy and Matplotlib, like this. As I said in the introduction, my goal is to give you an intuitive as well as a mathematical understanding of what is happening. We're going to implement all of the math ourselves. And for those of you who don't know what gradient descent is at all, it's essentially an optimization algorithm that we can use to find the minimum, at least the local minimum, of a function. And it's oftentimes used in machine learning to optimize weights and biases. So a very trivial example, a very superficial example, if I may use paint here for a second, is let's say we have a function in a coordinate system here. This is not going to be a beautiful drawing, but we have this coordinate system here. This is y, this is x. Let's say we have some very basic function like this maybe. Now, if we have a certain starting point, and in the context of neural networks, this gets more complicated because we're not working with just x and y, we're working maybe with 1,000, 10,000 dimensions. So this gets way more complicated, but the basic idea is we have some starting point for x. In this case, x is just the only variable. In neural networks, we have thousands, 10,000 weights and biases. All of them would be their own x, so to say, and y depends on all the weights and all the biases. Here we just have y depending on x, so it's a very simplified version of gradient descent. But we have a certain position where x is currently at. And in the context, again, of neural networks, this would be the current weight, the current value of a weight, for example. We want to adjust the weight so that the weight, so that this adjustment decreases the cost function. So we want to find, we want to get to the lowest possible point of y. So what gradient descent does, visually speaking, and we're going to go into the math here, in a second, but essentially we're trying to move x so that, or we're trying to adjust x so that the y value decreases. So we're going to see, okay, in order to decrease y, I have to increase x. So I do that, and by doing that, this ball, so to say, rolls into this valley, into this local valley. Once I reach this, or once I almost reach this minimum, I'm never going to reach it because I'm using a learning rate, I'm stepping closer to it, I'm converging this point, but I'm not actually reaching it. However, I'm not going to go further because then I would increase the function again, which means also that I'm not going to find the global minimum here. But this gradient descent technique is enough to get me into a local minimum. And now you have to imagine this for multiple different variables in higher dimensions, but we're going to today just use a 2-dimensional and a 3-dimensional example. And I actually can show you what the code is going to look like in the end, since I already implemented this. This could be gradient descent in 3 dimensions. So you can see here, this point is rolling down to this local minimum, as you can see here. That is gradient descent in 3 dimensions. This is what we're going to implement today, and we're going to do it completely from scratch. So we're going to import NumPy as NP, and we're going to import Matplotlib as PLT. So maybe let me turn off Copilot here. And we're going to just define a function here. You can optimize whatever function you want. This is in neural networks, this is going to be the cost function. So essentially the difference between the target value of the output neurons versus the actual values. But we're not going to focus too much on neural networks here. Gradient descent does not have to be used only in neural networks. The process in neural networks with backpropagation and so on is a little bit more complex, but it can be used to just find the minimum of a function. The reason why we use it, maybe as a context here, so that you understand the utility of it, is because it's very easy to just find the derivative and to find the minimum of a function in 1, 2, or 3 dimensions, or actually 2 or 3 dimensions. It's quite hard to do that in 10,000 dimensions, and because of that, we can just get closer and closer to it without having to compute it mathematically, which would be very difficult. So what we're going to do is we're going to just define a function, y function. It's going to depend on x. And for example, we can go with something very simple, x squared. So we just defined a function x squared, which is just this u shape. And we want to find the minimum of that function. Now, in order to find the minimum, in order to progress towards the minimum, we need to compute the derivative of the given function. So maybe let me use Paint here again. If I have the function, for this, you need to have at least some basic understanding of calculus. You don't have to be a professional and you don't have to understand everything, but you need to understand what the derivative of a function is. So when I have a point here, and let's say this is x squared, the derivative of x squared in that particular point is essentially the slope. Oh, no, this doesn't look too good. Maybe let me use this here. Is the slope. So basically how steep the function is at this point. And since this is a positive value in this case, because you can see the difference here is a positive value, this would mean that the direction of steepest descent is to just increase x. By increasing x, I increase y. By decreasing x, I decrease y. And the absolute value of that, so this is going to be a number, for example, let's say it's going to be maybe 8 or something. In this case, this would mean that one step into the x direction causes 8 steps into the y direction at that particular point. So in order to decrease the value of y, in order to decrease the output, what we need to do is we need to move x into the opposite direction. So if the direction is +8, plus meaning, the direction is basically binary. The direction can be plus or minus. So the sign of the derivative of the gradient is just the direction. And the absolute value, in this case 8, tells you how sensitive the y function is to this value being changed at this particular point. So in this case, the gradient is, gradient, we don't have multiple variables, so it's just a derivative. It's the slope of this function. It would be 8 into the positive direction to increase y, and I can just go the opposite direction, so -8, so to say, to decrease y. And we do that usually with a so-called learning rate because we don't want to just completely jump into the other direction. We don't want this to overshoot and end up here, for example. Because of that, we multiply this with a small number. So for example, the learning rate, I don't even know what this Greek character is called. It looks like an n. I'm not sure if it's n, probably something else. But essentially, we take a small step into that direction. And of course, the larger this value is, the larger the step is going to be. And the learning rate can be adjusted. We're going to see here in a second. Don't be too confused by my ugly drawings here. We're going to see what this looks like then when we have the visualization. But that's the basic idea. We need to compute the derivative of the function. We need to calculate it in this particular point, and then we need to go into the opposite direction, a small step to progress towards the minimum. So what we need to do here first is we need to have a function, which I'm going to call y derivative, which is going to take x, and this is just going to return here now, in this case, 2 times x, because that is just the derivative of x squared. If you don't know this, if you don't understand why this is the case, this video is probably not for you because you don't understand calculus at all. You need to know what a derivative is. You need to know how to take it. You need to know that x squared, the derivative of x squared is 2x. This is very basic knowledge. So we now have the derivative, we have the function. Now let's generate some values. Let's say NPA range. Generate values from -100 to 100 with a step size of 0.1, for example. And the y values are just going to be essentially all of these values squared, because that is our function. So y function of x. What we want to do now is we want to, maybe let's just plot the function before we do any gradient descent here. So plt plot x and y, plt show, this should show the function. What did I do? Oh, matplotlib.pyplot as plt, sorry about that. This is the function now. And of course, if I have a point here, the goal is to have this point rolling down to the minimum. So let's give a random point a starting position here. So let's say the starting position, or maybe let's call this a current position. The current position is going to be maybe something like 50 and then y function of 50. And we want to show that we want to show this point here as well. So plt scatter current position 0, current position 1, and the color shall be red, for example. So, okay, maybe this is too close to the minimum. Let's go with 80. There you go. So we have this point here. We want this point to roll down to the local minimum. In this case, it's also the global minimum. And how we do that is we just define a learning rate. We're going to call this learning underscore rate. Let's say this is 0.01. You might know this parameter from machine learning. Oftentimes when we create a neural network, we optimize it, we compile it, we train it, we need to specify a learning rate. This is basically the idea here as well. We specify how fast we want to move closer to the minimum. So that's that. And let's go ahead now and say that we want to have n amount of iterations. Let's say 4 placeholder in range, and let's go for 1,000 iterations here. What I want to do is I want to say the new x position, the new position of this coordinate here, of this value here, is going to be taking the current position and moving a tiny bit into the direction, into the opposite direction of the derivative. So I'm going to take the current position x, and I'm going to subtract from it. This is already the fact that I'm subtracting here means I'm reversing the direction, because usually what I would do is I would say plus learning rate times derivative, and then I would move up and up and up. But if I say negative, so if I say minus learning rate times derivative, so y derivative of current position 0, this means I take the derivative, I take the direction of steepest descent, I multiply it with the learning rate so that I take a small step, but I go into the opposite direction. This is why I have the negative here. This is why I have the minus here. And this gives me my new x value. So I adjust x so that I decrease y. That's the basic idea. And for that, we're going to also say then new y equals y function of new x to also calculate the new y value, and the new position in general, or we're going to call this current position here again, is going to just be new x, new y. And then the process repeats all the time. Now we're going to take all of this here, we're going to put it into the loop. I'm going to remove the show because we want to animate the process. So I'm going to say plt pause 0.001, and every time we want to clear the figure afterwards. So you can see what happens here. The ball rolls down towards the local minimum and the global minimum in this case as well. And you can see it never actually reaches the minimum, it converges towards it. And what we do in neural networks when we train them is we basically say, okay, if the decrease in the loss is very, very small, smaller than some epsilon, we basically say, okay, it's enough. You don't have to train further. You don't have to converge more. That's the basic idea here. Very simple in 2 dimensions. Now let's go ahead and change the learning rate to see what this actually does. If I add a bunch of zeros here to make it smaller, you will see that I barely make progress. You can see the ball still rolls down. I mean, hopefully you can see that. It still moves a little bit, but it's very, very slow. It's very slow, and there is no progress almost at all. If I remove some zeros here, it's still slower than previously, but it makes some movement, and it will end up here in a reasonable amount of time. Now, what happens, why shouldn't I just increase this? If this basically means that the higher the learning rate is, the faster I converge, why not just set this to 20? Now, I can set this to 20, and you will see what happens. Basically, this happens. This is complete nonsense. I mean, it just diverges. And you can see even Python gets an overflow error, int too large to convert to float. This is just not reasonable to do. And this already happens, I think, when I go for a 1. A learning rate of 1 oscillates, I mean, it doesn't diverge, but it oscillates, because basically what happens here is, it is at a certain point, maybe I can use this animation here. It is here, and it recognizes that this is the direction where I can decrease y. So I just take a massive step into that direction, but then I end up here. And then it recognizes that the best direction to go into is right. And then it jumps here, jumps back here again, because the step size is just too large. I think maybe if we go with 0.8, I'm not sure if this is still going to happen. Then actually it converges quite quickly, but this is only because this is a very simple function. But usually something around 0.001, 0.0001 is not too bad. So this is a good result here. Maybe before we go into 3 dimensions, we can use a different function. Maybe we can go and say we want to have the sine function here. And for this, we're going to use np sine, numpy sine. The derivative of the sine function is cosine. So here we would have np cosine of x. And then we should also change the range here from -5 to 5 with a step size. This is still fine. And we're going to start here at maybe 3. So you can see here, this works in the same way. Now, maybe let's change this from 3 to 1.5 or something. Yeah, there you go. So what you notice here is, I mean, this is quite slow. Maybe let's change this. You see, by the way, here, since this is not too steep, it rolls down very slowly, and the steeper the function is, the faster the ball rolls down. So you can see now it gets faster and faster because this is way steeper than this almost flat point at the function up here. What you notice here is that if here was the global minimum, let's say this function goes down and down and down and down, it would still roll into this local minimum. So it doesn't find the optimal solution every time. But that's always the case. So what you do usually is you have different initializations. One time you start here, one time you start here. You do that randomly, and you do that for multiple dimensions. But the intuition is the same. So let's go ahead now and turn this into a 3-dimensional visualization. So I'm going to call this main 3D. We're going to, again, just import numpy snp. We're going to import matplotlib.pyplot as plot. And now we're going to define a z function, which depends on x and y. And we're going to do that by saying z function, x and y. And we're going to return here. I'm going to use a fancy function right in the beginning. So I'm going to say return np sine 5 times x times np cosine of 5 times y divided by 5. Now, this is just a complex function that has a bunch of waves in it. This is the one that I showed you in the preview, or when I showed you the 3D visualization. This is the function here. You can compute the derivative yourself if you want to. You can also use some computational engine. But the derivative here is essentially just, I'm going to call this calculate gradient, because now you have partial derivatives, which is maybe a bit more advanced than just the ordinary derivative. So maybe not all of you guys have heard about this already. But if you have a multidimensional function, z, which depends on x and y, you can compute the partial derivative with respect to x and the partial derivative with respect to y, and you get different formulas. So for the gradient, we need both of those things. We need to return here, and this is now the result of taking the function, taking the derivative of that function with respect to x. The result of that is np cosine of 5 times x times np cosine 5 times y. This is with respect to x, and with respect to y, what we get is negative np sine 5x. And here you need to use the product rule and stuff like that. So it's maybe you don't understand why this is the case immediately, but you can go through the calculations and you will see that this is the result. But you just say np sine 5y. So that is the this is the x derivative, this is the y derivative, so this is the gradient vector, so to say. And of course, in machine learning, in neural networks, you have 10,000 different such derivatives which form the gradient vector, the gradient of the cost function usually. So what we do now is basically the same. We say x equals np arrange. We're going to go from -1 to 1. We're going to use a step size of 0.05. We're going to do the same thing for y. You can, of course, come up with your own function. You can also just use something like if you want to use a simpler example, you can go with NP, or actually not NP, you can go with x squared plus y squared if you want to. I just use this function because it's a little bit more complicated, and we can look at the movement of the ball and see which way it takes. So basically, we now turn this into a mesh grid, because if we just have x and y, we have just lines of values. We want to have a grid of values, and for that, we're going to say capital X, capital Y is going to be NP mesh grid of x and y, and z is just going to be the z function applied to capital X and capital Y. There you go. And now what we do is we say axis equals plt.subplot. We're going to set the projection to 3D, and I'm going to just say x.plot surface, x, y, and z. As a color map, we're going to use Viridis or Viridis, I don't know how it's pronounced. And we're going to say PLT show. This is now not gradient descent, this is just plotting the function. This is the function that we have now. In your case, if you chose a different function, you can visualize it the same way. You still need to do the mesh grid, but you can use different functions. And essentially what we want to do now is we want to see that, because those are all the same, so those are all local minimums, but also the same minimums, or equal minimums. What we want to do is we want to spawn a point somewhere here, and we want to watch it roll down into one of these minimums. So what we're going to do for this is we're going to set an initial position. We're going to say current position is going to be, let's say 0.7, 0.4. This is the example that I used in the beginning of this video. And we're going to just call the z function on these values, 0.7, 0.4. Or actually, yeah, 0.7, 0.4. So what we want to do now again is we want to define a learning rate. Learning rate is going to be 0.01 again. And then we want to go 3 iterations again. So for placeholder in range 1000. And usually what you do is you don't specify 1100. You specify a tolerance. So for example, if the loss changes in a meaningful way, you keep rolling and rolling and rolling. But if you realize that the loss changes and improves just a tiny, tiny bit after a certain threshold, you just stop training because it's already good enough. So it's not worth it to do all the calculations again just to get an inch closer to the minimum. So with each iteration, we want to plot the surface, but we also want to plot the actual point. So we want to use scatter, current position 0, current position 1, current position 2. So X, Y, Z. The color of this is going to be magenta or magenta. And of course, we need to do the calculation here again. So we need to compute the gradient, and then we need to move the values into the direction. So we're going to say X derivative, Y derivative is going to be equal to calculate gradient of current position 0 and current position 1. So it's the same position. We get the derivative with respect to X, with respect to Y. And then what we do is we say X new, Y new is going to be equal to whatever X is at the current moment. So current position 0 is the X value minus the learning rate times the derivative with respect to X. And we do the same thing for Y. So we get the current position 1 minus learning rate times Y derivative. So we basically compute the gradient, the direction of steepest descent. We go into the opposite direction with this factor learning rate, and we just move X and Y so that Z decreases in the best possible way, in the fastest possible way, given the learning rate, of course. So what we do then is we say current position is X new, Y new, and Z function of X new and Y new, like this. And I think it makes sense to put this into a tuple, right? I'm not sure if that's redundant, but we're going to do it. All right, so we have the new current position. So all we have to do now is we have to say PLT pause 0.001, and we want to clear the axis every time that we make a new plot, or we made a new plot. So one thing that you will notice here is that we cannot really see the point. I mean, we can see it, but it's not very visible, so it's not clearly visible. What we need to do in order to see the point properly is we need to change here one parameter called computed underscore z order. We're going to set this to false because what basically happens is that the point will always be in the background of the function, no matter if it's actually above the function, on the function, below the function. We will never see it clearly because the function is always prioritized. We can manually change that by just adding a z order here of 0 to the surface plot and a z order of 1 to the scatter plot, meaning we prioritize the point and we always see the point no matter what direction we look from. Even if we look from below, we can see the point. And you can see how it rolls into this local minimum. There you go. That is gradient descent in action here. Now, maybe it can be interesting to, this is now not part of my prepared code anymore. I hope I still don't mess it up. Maybe we can just simulate multiple points. So maybe I can go and say current position, current position, current position. Maybe I can call this 1, 2, 3. We start at different points, 0.3, 0.8, 0.5, 0.5, something like that. Or maybe we can go with negative 0.5, 0.5. And now instead of doing just this, we're going to do this for all the different points. So current position 1, 1, 1. Then current position 1 is that. Here we plot current position 1, current position 1, current position 1. And basically, I think it should be possible to just copy this, to change everything here to a 2. Here as well. Here as well. If I forget 1, 2, everything will be we'll have errors. Let's change everything to a 3 here, not to a 4, to a 3. There you go. And now basically we just have to repeat this line here for 2, for 3, for 3, for 2, for 2, for 3. And maybe we can go with green here, and we can go with cyan here. And then we should see 3 points at the same time going through the process of gradient descent. There you go. And you can now repeat this for as many points as you want. Those two end up in the same minimum. This one ends up here. In this case, it doesn't really matter because all of them have the same value for z, but one of them could be better than others if one of them goes down more than the others. But yeah, this is how you implement and visualize gradient descent from scratch in Python. So that's it for today's video. I hope you enjoyed it and hope you learned something. If so, let me know by hitting the like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching. See you in the next video and bye.